So the next thing that we have to cover involves discussion now, not just of what a population is or what the frequency of alleles are, but how is the population growing or perhaps shrinking in terms of density and numbers of organisms. So although this seems like it's separate from what we did at the beginning, remember that how many organisms there are have a huge impact on what's in the gene pool. So we're just looking at this from a different aspect than we were before. So we're going to start our discussion by talking about population density. We might start talking a little bit about growth today, but the focus today will be density. So if I want to know how a population is growing, I have to know what I have in the beginning. And sometimes just a number is not a good indication of whether the population is thriving or not. So instead of just including how many there are, we're going to consider how many there are in a particular space. So population density could be defined as the number, which is n, of organisms in an area, which would be the A, or a volume, which would be the V. You don't have to memorize the formula for density. It is on your data sheet. You might remember learning about density in like grade 8 science, where you were calculating the density of like a substance. So we're doing the same kind of calculation. How much is there over how much volume? But now we're talking about organisms instead of about atoms or molecules. So it says population density, number n of organisms in an area, A, or a volume, V. All right, so you have two different versions of the formula that you could possibly use. One is where you take the number of organisms, n, and divide it by an area. The other is divided by a volume. Unlike, say, chemistry, where it is really important which unit you are using, and you sometimes have to change the unit before you do a calculation, you are going to use whatever units you get in the question. So there's no need for you to change the units to meters or to grams or to kilograms or whatever the case may be. You're going to use the units that you get. So in the example that I have at the top here, it says you find 12 insects in an area of 10 meters squared. So this is my n, and this is my A. So if I want to calculate population density, I'm going to divide the number of insects by the area in which I found them. So 12 insects divided by 10.0 meters squared. Now, some of you will wonder, oh, do we have to consider significant digits if we're calculating things? The answer is yes, but if we're asking you to calculate something and it's a numeric response, the question is going to tell you how many digits to use. So you won't have to guess how many digits to include. In addition, if this was a numeric response question, so numeric response questions always have blanks, it will tell you the unit that your answer should be in. So if this was a numeric response question, it would say blank, 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 insects per meter squared. So even if you didn't remember that this was on your data sheet, or you had no idea what N and A and D represented, it tells you insects per meter squared. So that's cluing you in, you got to divide the number of insects by the number of meters squared. In this particular one, it would tell you to put a 2-digit answer. And notice it won't say 2 significant digits, it'll just say 2 digits so that you know how many actual numbers there are going to be in the answer that you give. 12 divided by 10 is 1.2, and that is the answer that you would put were this a numeric response question. So always look for the clues, especially on numeric response questions. It'll tell you how many digits, and it'll tell you the unit, which will basically tell you which calculation you need to perform. The second example is just to show you how you could use volume. In this case, I get milliliters, that's a volume, And how many larvae? That's a number of organisms. So I have a V and an N. Even though I would continue to say it doesn't seem like the formulas are that difficult, by the time you get to the end of the course and you're trying to decide what to do, sometimes you forget what things mean or what things represent. So I would highly recommend when you get a question where you have to calculate something, try to identify what are the variables that you know at the beginning, and that'll help you pick which formula or which type of calculation you're going to use. So since I know V and N, that's what I'm going to use. So I'm going to do 54 larvae divided by 200 milliliters. Again, if it was a numeric response question, it would tell you how many digits to put. So I'm going to simulate this one. Now there are 4 spaces in a numeric response answer. The decimal could take up one of those spaces and often does. So in this particular example, the answer is 0.27 larvae per milliliter. The instructions for this numeric response question would tell you to put 3 digits in your answer. That's because the 0 is a digit. It's not a significant digit, but it's still a digit. So it's telling you how many numbers you should be filling in. You can't start numeric response questions with the decimal. You have to start it with a 0. Yeah. It's possible, yes. It's possible. It's usually not the main focus of biology diploma questions. Like that's typically not what we want you to do, but it is possible. Usually it's not with this formula. Usually it's with one of the later ones, and we'll do some examples of manipulating formulas with them. Does anybody want to ask anything here? So, to further your question, it would be rare that we would only ask you to calculate the population density. It's kind of a simple formula. So there's a couple of contexts in which you might see population density. One of them would be reading a graph. So I'm just going to sketch a random miscellaneous graph here where we have number of an organism here and we have milliliters over here, something like that. And maybe your graph looks something like this. It would be possible for us to combo up reading a graph and calculating population density at the same time. So let's say that I asked you in 200 milliliters, what's the population density? Well, you would say, okay, well, here's 200 milliliters. Let's say that there were 200 so that it's easy. You might have to calculate density after you've read a graph. And then that would be 2 things, 2 skills that we're asking you to do in the question. And I think that would be more realistic than only asking you to calculate density all by itself. There are some other contexts in which we would ask you to calculate density, but they'll have to do with some of the things we'll discuss later on in the lesson. Does anyone want to ask anything here? So if I calculate density, that's super great, but it doesn't always tell me where the organisms are. All I know is how many of them there are, but not necessarily where they are in their geographic range. So the next part has to do with distribution patterns. Now I have a picture for each one of them just so that you can get a visual of what each of these distribution patterns looks like. And there are 3 of them. The first distribution pattern is random. And the first thing I'll tell you is that it's uncommon. This is not a typical distribution pattern because the only way that this exists is when resources are plentiful and competition is minimal. And there are not a lot of scenarios where organisms have easy access to resources wherever they are and also have little competition with other organisms. Now, just because it's not common doesn't mean it never happens. And so an example that you might see, and I tried to pick examples that were close to us, would be a moose in the prairies in the summertime. And it's important that it's in the summer because that is when plants are more abundant, resources are more easily available. But you might see a bunch of moose, like I have depicted here, randomly distributed in an area. So I don't think that it's super likely that you will have to calculate area. It's not a main focus of this unit. But on the off chance that you do, I just want to remind you how to calculate area. Let's say that that square or rectangle was 10 kilometers by 15 kilometers. If I wanted to calculate the area, I would do 10 kilometers by 15 kilometers, right? So length times width, one side times the other side. And so that would tell us that the area is 150 kilometers squared. And then I could ask you to calculate the density of the population. So if we wanted to do that, if you count in my little picture there are 10 of them. So there are 10 moose divided by 150 kilometers squared. And that would be how we would calculate the density of the population. Now, is there anybody who wants to ask any questions about either area or maybe this first distribution pattern? So the distribution pattern informs us a little bit more. It tells us not just how many organisms there are, but where they are relative to each other. The second distribution pattern is clumped, and this one is the most common. If there was a distribution pattern question and you were left to guessing as your answer, guess this one. This is probably how organisms are distributed. It's how people are distributed. If you look at, they have these nice maps of Canada where they'll put like lights or something on the picture to show where people live. People don't live everywhere. We live close to water and where the temperature tends to be warmer and better. And then fewer people live in areas where the temperature is colder. But almost without fail, people live near a river because in the past that was necessary for transportation, or people live near a big body of water. So this is the most common. The reason they would be clumped is that they gather for shelter, protection, perhaps resources, anything that will help them survive. If it can be found only in one spot in the range in which they exist, they'll all clump there. So there are snails that exist kind of only near the hot springs. And the reason that they do so is because, let's imagine this was where the source was. It's warm. The stuff that they need to survive, a lot of the time there's a lot of sulfur that comes out when there's a hydrothermal source. And these type of organisms like high temperatures and sulfur content. And so they congregate around the source of a hot spring because that is where the resources that they require for survival exist. This would be true for most species most of the time. They're all going to group where water or food or shelter is available. So if you think, I think I mentioned this, we are on a Lion King binge at my house. We've been watching it incessantly. They're always at the water hole, right? The water hole is where you go. Everybody needs water, and lots of organisms congregate there. Does anyone want to ask any questions about this one? Yeah. Mm-hmm. Mm-hmm. That's a good question. It might give you a diagram. That's certainly possible. But what I think is probably more likely is that they describe to you what's happening. So the question might say, hey, snails all gather around the source of a hot spring. What type of distribution pattern is this? Or packs of animals travel in search of a watering hole so that they can find water. That would tell me that they're clumped because they're looking for a resource. Okay. So the last distribution pattern is uniform. This type of distribution pattern is usually found in what we would call an artificial population. So, for example, agriculture. If you think about when someone is planting grain or corn or something in a field, it is pretty uniform. They space things out, there are little rows, they're all distributed fairly uniformly in the field. Or in defense of territory. So the golden eagle is my example, but really any large predator might have a uniform distribution pattern. It might be hard to say that it's perfectly uniform, but it would probably be pretty close. Big predatory birds like this tend to stake out an area and chase off other birds that try to enter their territorial area. So there should only be one of them in a given area. And they usually spread out about the same distance apart from each other. So birds tend to have a similar range that they want to protect or that they want to cover. The defensive territory is probably, like I said, not perfectly uniform like a farmer's field would be, but it's as close as we would get usually with an animal. So if you look at this picture, I tried to put them exactly the same space apart, one from the other, so that you would see that it was uniform. Now that we know how many organisms there are in what area and how they're distributed, we can start to consider how the population changes. So there are 4 terms that will typically be included in questions somewhere, somehow, to indicate to you how population size changes. Natality, which starts with an N, and will be the little n down here, represents births. So how many organisms are born in a population in some specified amount of time. Immigration, which starts with an I, and will be the little I down here, represents new members arriving in the population. And we already mentioned this when we talked about migration and how that's something that changes Hardy-Weinberg equilibrium. Mortality is talking about deaths, and it's the little m down here. And emigration is when members leave the population. So these 4 things are typically included somewhere, somehow, in questions to help you determine how a population has changed. Now, if you look at your data sheet, you'll see that there's a little formula for delta n, but it doesn't have these little letters in it like mine does. What your formula says, I'm just going to grab a data sheet here to show you. So it's in the same box as the Hardy-Weinberg formula and the population density. On your data sheet, it says delta n equals factors that increase population minus factors that decrease population. So these 2 factors increase, and these 2 factors decrease a population. So what I did was put them into the formula that's on your data sheet. So we're going to take the things that increase minus the things that decrease. So it would be possible for us to just ask you a question about how the population has changed, but that's just one step. It's a little bit too simple. So what a likely question that I would anticipate would be something like, how has the density of the population changed? That means that you would have to calculate the density originally, figure out the change in population, and then calculate the density again at the end. So I'm going to give you a little example here. Let's say that we have 100 meters squared of area. And in that 100 meters squared, I have 12 ladybugs. And then after some time has elapsed, and you'll notice in this formula, the amount of time is not the important thing. It's not part of the equation. But at some point later on, the population changes. I have 2 that are born, 3 that die, 10 that immigrate, and 4 that emigrate. Smart board. So, what would you have to do in a scenario like this? My smartboard's having a seizure. Okay, I'm just not going to touch it because I'm not sure what's happening here. But you would calculate the population density here. And then we'll finish talking about this in our class next week.